with the solve. Final equation, find powers. But you don't solve from one limit, you solve linear order. Yeah. Did it ask these questions about like underdash, overdash? Yeah. Yeah. So they gave us three methods. It's not too different. Like using Newtonian, so whatever that's what you use. And then we have another one. Three methods. So we almost the same. You could understand letters, you could understand the problem things, but on the quiz it's gonna be something different. Just we'll solve the time limit. Yes, solve the ODE, the second degree, is that what it is? Like the X number. Equal to what? Yeah, that's from the constant. Yeah, I but the thing about LeBron, I don't like the it's called like partial fraction. Yeah, but it also it's guessing sometimes because you have to do the guess. Then you find the R equation. No, like you know, it's actually hard. After that, like, as soon as you're done with the homogeneous, as soon as you do the particular, you have to get. Well, I think you're talking about the yeah. So that's after A. First you find like you have to guess. You have to guess. You have to guess the first one. The only guess was method. Yes. So after A, B, C, whatever, how you just even. So you have like. But you just guess the form of the answer. So if it's a constant, if it's like that's the method in terms of I think it is. This is my you don't have to guess it. You do the same way. You do a little bit of math and you're guessing. It is. Where you at? Oh, yeah, we have. It was pretty easy. This team has got their money right now. Thanks to really resistant that. 3-0 last time. Fortunately, watch it. I really much happy. Moving the game. We were just like running.
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Doing good, doing good. All right, two more class sessions until spring break. So I'm sure everyone is excited for that. Right. All right, so today's gonna be our last lecture on time marching schemes. And so I have a couple sample codes I want to go with you over today. What's different about today is that you're actually going to see things actually change with time. And so, that might seem kind of strange, kind of where we were last week, but we haven't actually introduced time as a variable in our equations yet, right? So we have a time derivative, but we don't have actually anything changing with time. So we'll talk about what that means today, and we'll see kind of how that affects our results. Okay. Announcements. Remember, homework 4 is out there. So remember, homework 4 is due on Sunday. So make sure you please get it in before then. I'm not going to assign another homework assignment until after we come back from spring break. So I want you guys to, really, at least for this class, enjoy the spring break, not think about school at all. Because, I think we all need that purpose. Okay? And then after we come back, we'll pick up kind of where we left off. Right? Okay. All right. So I think that's all my announcements. Are there any questions I can answer before we get started for today? Okay. All right. So let's go and get started. And so the topic for today is going to be time varying properties and time varying boundaries. Oh, also, I brought the exams again. So if you haven't picked up your exam yet and you're in the classroom, you can come pick it up after the lecture. Okay. So let's review kind of what we've covered so far. So, for the last couple of weeks, we've been covering unsteady problems. Okay. And so what that basically means is that we're introducing a time derivative into our equation. So this has kind of been the star of the show for the last couple of weeks. We have partial phi, partial t. Okay. And so, before we embarked on this, remember we've had derivatives that we've dealt with, but our derivatives has always been in space, right? So we've had derivatives in x and y, but never t. Okay? So t is different, of course. And so the way that we solve these problems, the way that we deal with them, is we have to use a time marching scheme. Which is quite a different approach to solving our problems, because now we're still doing matrices, we're still doing linear solves, but the way that we kind of structure it all is a bit different because of that. Okay, and we went over two in particular. Went over explicit Euler and implicit Euler. Okay. And so we talked at length about what those two are, what the differences between them are, how do you implement them differently, and what are their properties. Okay. And so all that is good. So that is, that by itself is already a very solid foundation in solving for unsteady problems. Okay? And we've done quite a few examples along this vein as well. Today, we're going to do something a little bit different. And so, if you look back at all the examples that we've done so far, time actually has not appeared as a variable in the equation. Okay? So what do I mean by that? And so, you might look at the above term, you're like, wait a minute, time is right there. You literally just told us that time showed up in the derivative, right? And so how can I say that time hasn't shown up as a variable when it's, in the only thing that I've written here? This time right here is a bit different. And so this time right here appears as a derivative, okay? And so this entire quantity represents the rate of change of our solution with respect to time. That's different than having something in your equation actually changing with time, right? So on the one hand, we have kind of a rate of change with time, and on the other hand, we have time actually showing up, okay? And so what do I mean by that? And so some examples, okay? These are all examples that can happen in kind of real engineering situations. Maybe we have a convection velocity that changes with time. Okay? Okay, because normally what we're accustomed to, when I say convection velocities, I mean u and v, right? Normally we're accustomed to these having flat values or constant values, right? So we're used to the velocity being maybe the x velocity being 50 and the y velocity being 1. Okay, I don't mean that anymore. So what I mean by this is, maybe we have a u velocity that's maybe 50 cosine of t. and maybe a y velocity of, a sine of t, okay? So now our velocities don't have constant values anymore. Their values are going to change with time. And that's evidenced by the fact that, when we have expressions for these velocities, we see that we have time in these expressions. So that's what I mean by time showing up as a variable. So now time is actually going to show up in our, in our properties and also in our boundary conditions, okay? And so to handle these situations, our time marching schemes are still going to be the same. So we're still going to use explicit Euler, implicit Euler. We just have to do a little bit of extra stuff to keep track of what I call a time variable. Okay. And so most of what we're going to talk about today is, how do we define this time variable? How do we use it? And how do we properly maintain it as we go through the time marching scheme? Okay. Any questions on this? So the exciting thing about this is that, now our results are actually going to be full length videos as well. And so, you'll see when we run the two codes today, it's actually going to produce, I modified the MATLAB files to produce an MP4 file. And so that's a file that you can actually view and watch as a video. Okay. All right, question. So now we're changing both the time and location to represent the entire flow. Well, in this example, yeah, the flow is changing with time. And so you'll see in the examples that, as we go through the time loop, right, as we're looping over each of the different time variables, right, the value for the velocities are going to change based on that time. Yeah. But you can also have situations like kind of what we did for the first, for homework 3, where the velocities also change with location as well. So now we're changing both location and space. Okay, so let's jump right into an example. And then we'll see kind of how this is. And so in this example, I'm actually going to give you a case where the boundary condition is going to change with time. And so in this example, we're going to solve a 1D unsteady diffusion example. Okay, so this is actually going to be the same example that we did last time, except I'm going to make one kind of small change. Okay. So that's our governing equation. So we have partial phi partial t is equal to 3 partial squared phi partial x squared. Okay. So the boundary conditions, we need to have 2 of them, because it's a 1D problem. And so our boundary condition on the left, when phi is equal to, when x is equal to 0, this is going to be cosine of phi t. Okay. So there's our t, and so that's where t is going to show up here, is going to be in that boundary condition. Our other boundary condition is going to stay constant. And so we're going to have a constant Neumann boundary condition of 2 on the other side. Okay. And so our initial condition, we're just going to use a simple 0 initialization. So we're going to say at all values of x, when t is equal to 0, is going to be 0. Okay. So let's go ahead and march this system forward in time with implicit Euler. We also need our grid spacing and our time step size. And so we're going to assume, let's assume delta x is equal to 0.25 and delta t is equal to 0.1. Okay. And just to keep things simple, let's say our n here is 5. And so we're working on a grid of 5 points. Okay. Right, so that's the problem statement. So this is identical. So I think we did this example last Monday. And so if you look back in your notes last Monday, this is going to be the same. So I'm going to skip a lot of that work just because, we saw it before. And I'm going to skip ahead to kind of the matrix form and the recurrence relationship. But before I do that, are there any questions on just the problem statement here? Okay. All right, so let's go ahead and apply implicit Euler. And so when you're applying these time marching schemes, I've already given you kind of the general form, and so you can just kind of plug into it. And so in this case, we have u is equal to 0, k is equal to 3, delta x is equal to 0.25, and delta t is equal to 0.1. Okay. All right, and so you plug in all of those, and you get the following equation for the interior nodes. What we get for the interior nodes, we get minus 4.8, I minus 1 at n plus 1, plus 10.6 bi n plus 1 minus 4.8 bi minus 1 n plus 1 is equal to vi. All right, so let's go ahead and apply this to our interior nodes, as well as our boundary conditions. Remember, we need 5 equations. Okay? I'm going to apply this to interior nodes. So let me go ahead and write placeholders for all 5 equations. We have I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4, and I is equal to 5. Okay. Okay, so our interior nodes in this case is going to be I is equal to 2, 3, and 4. So let's go ahead and plug in for that. Okay. So at I is equal to 2, we have a minus 4.8, B1, n plus 1, plus 10.6, B2, n plus 1, minus 4.8, B3, n plus 1. All this is equal to B2 at n. All right, I'm going to do the same thing for I is equal to 3. And I is equal to 4 as well. All right, so far so good. So far, this is kind of the same as we did last week, right? So just like before, we get our explicit or implicit Euler equation, we apply that to all the interior nodes, and we get equations for those nodes. Okay. Let's do the boundary conditions now. I'm going to save I is equal to 1 for last, because that's going to be that's the only new thing here. Okay. So at I is equal to 5, we have our Neumann boundary condition. So what we have for this is phi5 minus phi4 divided by delta x is equal to 2. Okay. To make this into an implicit Euler equation, I'm going to take all these phi values and apply n plus 1. N plus 1, n plus 1. Okay. And so our equation for this one is going to be phi5 n plus 1 minus phi4 n plus 1 is equal to 2 delta x. Okay. Delta x in this case is 0.25, and so we end up with 0.5 on the other side. Okay. And so I'm going to write this down in our system here. So we have minus phi4 n plus 1 plus phi5 n plus 1 is equal to 0.5. All that is good. Okay. The last thing we have here is the boundary condition as I is equal to 1. And so if we look back at our equation here, okay, our boundary condition is given by this, right? So we have a Dirichlet boundary condition because we don't have a derivative here, right? So we're saying that we're directly setting the value for phi. Okay? And so our first equation here is going to be phi1 at n plus 1, okay, is equal to Normally we set a constant value here, right? So for a normal Dirichlet boundary condition, we say this is equal to like 0 or 1 or whatever. Okay. Now for the first time, we're actually going to change this with time. So according to our boundary condition, this can be equal to cosine times pi of t. Okay. Except, this time, because we're doing it in a time marching scheme, I'm going to add a little subscript here, okay? And so instead of just cosine of t, it's going to be cosine of pi t sub n, okay? For this t sub n here, this is our time variable. So all that looks good. So now that we have our time variable in there, now that we have all our equations, we're almost set to go. Okay. Before we jump into the code, before I show you kind of the example code here, I do want to prime you a little bit just to kind of show you, how do we actually maintain this time variable? What do we set it equal to? And then how do we update its value kind of throughout the code? Because that's going to be key to this kind of whole thing. And that's going to, and that's what makes this going to be different than what we covered last week. All right, any questions on this before we do that? Okay, so let's talk about how do we actually keep this time variable and how do we update it? Okay. First, let's talk about what that time variable there is meant to represent. That time variable, the Tn, represents the current time of the simulation. ran out of room there, but my pride didn't let me to go to the next line, so I just squished that in there. Okay, so what do I mean by that? And so remember, in time marching, we're solving for the solution one time step at a time, right? You can almost think of it as like, we're kind of constructing kind of all the frames of a video kind of one frame at a time. Okay. So let me show you what I mean by that. And so now I'm going to make a line here. And so this line is going to represent time. Okay. So don't get confused. I know above that I showed you the domain, but that's in space. Okay? So this is going to be in time. Okay. And remember, our time step size for this problem is delta t. So our delta t in this case is 0.1. And we can go ahead and add a unit to this, can be 0.1 seconds. Okay. So that means every solution frame that we solve for is going to be 0.1 seconds separated from each other. Okay? So this distance right here, or should I say this amount of time in between the first two nodes is going to be 0.1 seconds. Okay? This time right here, 0.1 seconds, 0.1 seconds, and so on and so forth. Okay. Usually for most simulations, we're going to assume that our time is going to start at 0. Okay, so the genesis of our solution is going to be at t is equal to 0. Okay. And so what the Tn then represents is that, for each of the following dots, that's going to show how much time has passed since we started the simulation. Okay. So Tn is equal to 0.1 here, Tn is equal to 0.2, Tn is equal to 0.3, 0.4, and so on. Okay. The important quality here is that each time step, each time that we march forward, or each step, I guess, moving forward in time, our Tn increases in value by delta t. I want to highlight the first part there, okay? And so when I say each time we march forward, another way that we can say this is that each time our loop completes. Okay? So every time our time loop completes, then we're going to increase Tn by delta t. Okay. And so in code, it's going to look like this. And so, there's a few things we need to do. And so first, we need to initialize our time variable. And we usually do this outside the time loop. So we're going to have some point in our code, we're going to have t. You can call it Tn if you want, but I usually just like to call it t. Okay. And so somewhere in our code, somewhere near the top of our code, we're going to have t is equal to 0. Okay. All right, step 2. After we initialize the time variable outside the time loop, inside our time loop, we can just go ahead and use it as our equations indicate. And so for example, in this particular problem, we're going to have one of our boundary conditions. Okay, so we have phi1 n plus 1. It's going to be equal to cosine of pi t. Okay. So as long as we create the time variable, we can just go ahead and use it in our equations. So step 2 is actually, it sounds long, but step 2 is actually kind of the easiest part. Okay. Okay. And then finally, step 3, this is probably the most important part. At the end of the time loop, but before the end, okay. At the end of the time loop, what we need to do is we need to update the value for t. Okay. So one thing you'll see in the code is we'll have t is equal to t plus dt. Okay. What we're saying with that piece of code is that we're done with this time, we're done with this instant of time, and so we're going to go ahead and loop again. But on the next time loop, our t value is going to be increased by an amount delta t. Okay. All right, so that's the essence of it. And so, right now, this is before we've seen the code, and so, this might seem a little bit dry here, but hopefully once we see the code, it's not too complicated. All right, any questions on this before we start looking at the code? Okay, all right, so let me go ahead and switch to the computer here. And this one, okay. All right, so this is our code for this problem, okay? And so what I've done here is I've set the coefficients in the left-hand side matrix, and so this is still the same, okay? And so I'm not going to go over this one again because this was from our example last Monday, okay? I want to kind of skip to this part right here. Okay, and so this is kind of where we introduce the time variable. And so the first thing that we set here is we set t is equal to 0, okay? And so this is kind of the first step that we just went over. So defining the time step value or the time value. Okay. Next, we're setting dt. And so this is the value of delta t. Okay. Or in other words, this is the amount that t is going to increase on each time step. We also use it in our equations. This is delta t. Okay. All right, and so finally we come to the time stepping loop. And so I have no idea why this is a while loop. I don't know why I did it this way. I might have done this. Someone must have asked me this a couple of years ago to put it in a while loop, but I'm just going to go ahead and cancel this out. Go. Okay, so this is the loop that we kind of are accustomed to. So we have our time loop here, right? And so our time loop is always going to look like this. And so it's going to be a for loop. Our t step is equal to 1 to nt, okay? And here's where the time variable comes into play. And so if you look at our system of equations in your notes, right? The right-hand side of the first row is going to be cosine of pi t, right? And so this is where we're using it. So we have b, where b here represents our right-hand side vector. We're setting that equal to cosine of pi times t, okay? And since we're maintaining this t variable now, this is going to change in each time step. Okay. Okay, so besides that, we have our interior nodes. Remember, for our interior nodes, we have phi I at n on the right-hand side. Okay. We have our linear solve here. So we have a backslash b. Then we have our update here. So we have, once we solve for it, our current solution is equal to whatever we solve for next. Okay. And then we plot it. Right, so that's all going to be the same. I have a little extra code here to save it as a video file, which I'll show you in a bit. Okay. And then finally, we come to the end of the time loop here, which is where we're updating our time variable. Okay, so remember, this is always important when you have things that change with time. You have this line of code here at the bottom. So you have t is equal to t plus delta t. Okay. Okay, so let's see what's going to happen. And so what we expect is that because our Dirichlet boundary condition is changing with time on the left, it's actually changing as a cosine function. So actually, you're going to see this this solution here is going to wiggle and vibrate. Okay, so I'm going to hit and play, and there is our solution. It's kind of wiggling like that. And actually, I saved this as a video file, so let's go ahead and view that. Sure, Windows Media Player. Okay. All right, so it's going fast. Let me see if I can just loop this really quick. Okay. And so what you're seeing here, it's a little bit hard to kind of see here, but on the left-hand side right here, do you see this, the Dirichlet value here is vibrating up and down, okay? And so because we set the Dirichlet boundary condition there to be a cosine, that cosine is going to vibrate between, 1 and -1, until we basically tell it to stop, right? And then what's happening for the rest of the solution is that it's kind of following its lead, right? And so what we have is a simple diffusion equation. And so, that change in the boundary condition on the left is being diffused over to the right. And so what it kind of looks like here is kind of a vibrating string. Okay. All right. And all of that was made possible due to kind of that small adjustment that we made to the code where we have that the time variable. Okay. Any questions on this? Okay. All right. And so, of course, there's the while loop version of that too. So this code is all posted online. So it's there for you to see. Okay. All right. Question. So will the problem always give us a delta t, or do we have to find it by ourselves in some case where the problem gives us some sort of info? So there is a methodology for you to solve for delta t. But for this class, I'm always going to give it to you. So in the problems that you're going to do in this class, delta t will always be given. That's basically just to make sure that you always have a stable solution, and it kind of just simplifies that for you. So yeah, so delta t will always be given to you. Okay, all right. So let me go ahead and bring it back here. All right, so that was a 1D problem, and so that was a 1D problem with a time varying boundary condition. Excuse me, sorry. So that was same location, different t. That was actually the entire domain. And so that was because that was a 1D problem. And so we're seeing the solution at all 5 points at different values of time. Yeah. Okay. All right, so let's do another example. Let's do a 2D problem now, but this time let's have one of the properties change with time. So let's have a 2D problem with a time varying velocity. Okay. All right. All right, so our equation is going to look like this. So we have partial phi partial t plus 50 cosine of pi t, phi partial x plus sine of pi t partial phi partial y is equal to 3 partial squared phi partial x squared plus partial squared phi partial y squared plus 3xy. Okay. And so, of course, the big difference here is the fact that we have these two, they're embedded into the equation now. So this 50 cosine t pi t, that's going to be our u. Our v in this case is going to be a sine of pi t. Okay. Okay. And so this is going to be solved on the following domain. Okay. And so I believe we did this example last Wednesday, except without the u and v, of course. All right, so we're going to have 30 by 30. So 30 nodes in the x direction, 30 nodes in the y direction. We have phi is equal to 25 in each on the east and south boundaries. And then we have a Dirichlet boundary condition of phi is equal to 50 on the top and left boundaries. Okay. So for the time parameters, we're going to have delta t. In this case, it's going to be 0.1 seconds, and nt is going to be 500. Okay. All right, and so what we want to do is we want to advance the system forward in time, and we're going to use the implicit Euler method again. Okay. And this will actually be the first example that we do, which is with 2D implicit Euler. Okay, so I think that was one example that was missing from the notes last time, and so I wanted to make sure I do a 2D example with implicit Euler today. Okay, so let's go ahead and get started with this. Okay. Well, first I do want to make a note. Okay. Because the properties of our equation are actually changing with time, that means that when we compute our left-hand side matrix, the values in that matrix or the coefficient in that matrix are going to change with time as well. Okay? And so we need to recompute that in every time step. So this is quite different. So this is probably the biggest change that we're going to make compared to the code we saw last week, right? And so last week when we did these unsteady problems, we kind of, if you look at those codes, we pre-computed the matrix coefficients before we enter the time. Okay, that's to kind of save us some time. Okay? This time, because the u and v, the values for u and v are going to be changing each time step, we need to recompute the matrix coefficients each time step. Okay, and so this time you're actually going to see a loop within a loop within a loop. And so it's a triple nested format. So we're going to have the time loop up top. That's going to be our outermost loop. And then we have our loops on I and j inside of that. Okay. And then we have the boundary condition loops in as well. Okay, so this is probably the most expensive code that we're going to run. One of the most expensive codes we're going to run together in the class. Okay, but this code right here is also actually a very good precursor for your final project as well. Okay, so I'm working on your guys' final project right now, and so I'm hoping to have that ready for you guys to look at once we come back from spring break. Okay, and so if you can understand this code right here. And really get it to work really well and kind of understand every aspect of it, you're going to be in really good shape for the final project, because the final project is going to be, I mean, different than this, of course. It's going to be more stuff on top of it, but very similar structure. So it's going to be a 2D unsteady implicit Euler equation. Okay. All right, so with that, now that we kind of know what we need to do here, let's go ahead and write down our 2D implicit Euler formula. So we've only just written this formula down. We haven't actually used it in an example. So let me go ahead and write out the whole equation again. Okay. We have minus u delta t all over 2 delta x, k delta t x squared. Okay. This is phi I minus 1 comma j and plus 1 plus u delta t divided by 2 delta x minus k delta t divided by delta x squared, bi plus 1 j and plus 1 plus minus v delta t divided by 2 delta y is k delta t over delta y squared, I j minus 1 and plus 1. Okay. V delta t divided by 2 delta y. It's k delta t squared. Bi j plus 1 and plus 1. Okay. I know it's a mess, I know, but remember, we're not actually computing these for 2D problems. We're inputting these formulas into the code. Okay, so what's important is kind of what's in the parentheses in front of each phi term. Okay. So then for the last one, we have 1 plus 2k delta t divided by delta x squared plus 2k delta t y squared bi comma j plus 1 is equal to bi comma j at n plus q I comma j. What's important here? Okay. So remember, what's important here, remember the way that we actually use these equations, that we use this formula to actually get an equation, right? So what's actually important here are the formulas for each of the coefficients of the features. Okay? And so each line here, we're going to have basically 5 coefficients that we need to worry about. So we have the right neighbor, or excuse me, the left neighbor, the right neighbor, the bottom neighbor, the top neighbor, and the node itself. Okay, and we're going to input those directly into the code. Okay. And just a reminder, so since we have an implicit method, this equation right here, when we apply it to every single node in our grid, is going to get us a system of linear equations that we need to solve. Okay? So our system looks like this. So we have A, phi, I, comma, j, n plus 1 is equal to phi, j at n plus q at xi, yj plus whatever is stuff for the boundary conditions. Okay. Where this A here, this is our matrix of coefficients. And this has to be recomputed every single time step. All right, any questions on this so far? Okay, all right, we're actually doing pretty good on time today. So I want to try something a little bit different. Because I think usually when I do these examples, we work things out by hand, and then we kind of just jump straight into the code. And so, because of the kind of display limitations here, there's only so much of the code that I can kind of display at once. And so, I kind of feel this too when I'm kind of reading through the code. It doesn't feel very helpful because I'm kind of jumping between different parts of the code. And I'm showing you how I did stuff, but then, you don't really see the whole thing. So what I want to try now is I wanted to try, I'm going to give you kind of the general structure of the code, and we'll write it down here in the notes. Because, these codes are starting to get pretty long, right? And so I don't want you guys to get lost in the details. I want you guys to at least have a good idea of the overall structure of the code before we kind of jump into the details of seeing it. So let's see how this code is structured first, and then we'll jump into the details. Okay. So let's talk about the overall structure of the code that you're going to see when you open up the example file. Okay. All right. And so let's start at the very top. And so at the very top of the code, I always have section 1. Okay. And so section 1 of the code is setting, always setting kind of global variables, right? So these are things like the number of nodes, the time step size, the diffusion constant, setting up the left-hand side, right-hand side vectors, okay? So I'm not going to say too much on this because this is more or less the same. Okay? So this is going to be setting important parameters. So things like delta t, and x, and y, yada, yada. Okay. We have things like LHS matrix, which I think in this problem, I think I just use A. Okay. Is equal to zeros, yada, yada, right-hand side vector, zeros, yada. Okay. So same as always. And so there's nothing much different of that section of the code. Okay. Just any variable or any parameter that we're going to need to use throughout the code, we're going to set its value here. Okay. The only difference, we're not going to set a value for the velocities. Okay. So x velocity, y velocity, u and v, I'm going to leave that out of the section because remember they're changing every time step. Okay? Okay. All right, so that's section 1 of the code. So that's kind of more or less the same. Okay. Section 2. So section 2 of the code, this is where we're going to jump just kind of straight into the time. Okay. Whenever you have an unsteady code, you have a time loop that's going to move over all of your time steps. Okay. And so in this section of the code, it's going to say for t step is equal to 1 to nt. Okay. So that's kind of the header for our time loop. So that's basically telling you that we want this code, or we want the time loop to repeat nt times. Okay. But there's a couple of things that we actually do before we jump in, right? So the first thing that we just learned today is we need to set the time variable equal to 0. Okay, so we're going to set t is equal to 0 there. We also need to create variables for the current solution, so cur. Sol next as well. Okay. Right, so cur, remember this is vi comma j at n, and this is vi comma j n plus 1. Okay. Okay. So far we haven't actually done any computing yet. We've just done all the setup, right? So sections 1 and 2 we've just done the setup. Now we're getting into kind of the main part of the code where we're actually going to be computing stuff. Okay. All right. So inside the time loop, once we're inside the time loop, remember this. So everything that we do now until we reach the end statement, right? And so until we reach kind of the end of the time loop, we're going to be repeating every single time step. Okay. We're inside that time loop. Okay. Okay. So there's a few things we need to do. Okay. First thing we're going to do is we're going to kind of remember the fact that our velocities are changing with time. Okay. And so the first thing, so I'll do this section 3 here is going to be very large because we have a lot of stuff to do inside the time. Okay. Okay. And so the first thing we're going to do is we're going to update the values for the velocity. Okay. And so we're going to say x velocity. Actually, I don't remember what I put in the code. It might just be u. Okay. So x velocity here is going to be 50 times cosine of pi times t and y velocity is equal to sine of pi times t. Okay. Right. That's valid here because, you know, the t, we're going to basically update the value for t at each time step. And so if we have this formula here, then these are also going to update every time step as well. Okay. All right, so the next thing we're going to do inside the time loop is we're going to compute the values in the coefficient matrix. In this case, it's A. I guess that's the variable that I gave it to. Okay. And so for this one, just like we always do in 2D problems, whenever we're computing the coefficients in the matrix, we have to do this by visiting every node. And so remember the way we do this is we loop over all values of I and j. Okay? And so here you're going to have another loop, another two loops actually. So hopefully that looks familiar, right? And so when we're visiting all the nodes, we do it by a nested for loop. And so we have one loop over I, another loop over j. Okay. And then inside here, we have ID, we have a bunch of ID equations. Okay. All right, so I'm not going to write all of it down because you'll see that in the actual code. And then once we compute all the IDs, then we make the changes to the left-hand side matrix ID, comma, yada, 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 is equal to yada, yada, yada. Okay. Remember, these expressions here, or what we plug in here, these are based on our implicit Euler 2D equation from phi. And the last thing we need to do is we need to set the values for the right-hand side vector as well. Okay. And this also is based on the equation above. Okay. Okay. Any questions so far? So hopefully this kind of is making kind of logical sense, right? And so we start every code, we define all the important parameters. Okay. Then when you have a time marching code like this, you have a time loop, and then inside the time loop, we need to compute all the matrix coefficients, and that's kind of where we are right here. Okay. So remember, the goal for every code like this is we're kind of building up, we're kind of constructing all of the coefficients, all of our equations to solve at the same time. Okay. And so, think of it as, we're not actually solving anything, we're setting it up for the computer to solve. Okay. So that's a big part of the code. And so, that's going to be most of the work is going to be. Okay. And so after this, and so after the IJ loop ends, So after the end of the ij loop, we need to assign the boundary conditions. And so we're gonna have 4 loops here. Or 4 loops, I should say. One for each boundary. For I is equal to da da da. And then maybe 4j. Yada. And okay, and so on and so forth. Okay. This will be a fairly lengthy part of the code just because we have four loops to do. But you know, again, this is also kind of very similar to what we've done before. Okay. Section D. So we're still inside the time loop, and so we haven't left the time loop yet. Okay. But at this point, after we've assigned all the boundary conditions, all of our coefficients are the same, are computed at this point. So the left-hand side matrix, the right-hand side vector, they're all fully specified now. Okay, so we can go ahead and solve for sol next. So what you'll see is we have sol next is equal to left-hand side matrix backslash right-hand side vector. Okay. And of course, we need to update our solution. So we say the current solution is equal to sol next. Okay. So now that we solve for the current solution, we are ready to plot it. Okay. Don't worry about this part. I've already written the code for plotting for you, but you know, in case you were curious what it is. Okay. So do not worry about this. Matata. All right, the last part, very important. And so, you know, don't forget this part when you're making an unsteady code. Update the time variable. It's very easy to forget because it's literally the last thing, and you work so hard to do the all the coefficients and all the boundary conditions. So it's always forget. I trust me, I know. I forget it all the time too. But you cannot forget this. We have t is equal to t dt at the bottom. Okay. All right. And then finally from there, we have an end. And so this end at the bottom here is the end of the time loop. Okay. And I think after that, I might have a couple lines just to clean up the videos and things like that. All right, so you can see the majority of this code we're actually going to spend inside the time loop. So there's a lot we need to do. So whenever you have properties that change with time, you need to have all this stuff inside the time loops, that all your coefficients and boundary conditions can be computed properly. Okay. Okay. So that's kind of the plan. And so that's kind of the structure of the code that you're going to see. Right? So hopefully going through that by hand was helpful. You know, just so that you can have it in your notes. You know, this ended up actually being not as helpful because, you know, you have to kind of scroll a lot to see it all, but, you know, hopefully you have it all in your notes so you can kind of see it as we kind of review the code live. Okay. Any questions on this before we jump into the code itself? Okay. All right, so let me go ahead and share my screen again. Okay, so let's look at the other code now. So let's close this figure. Okay, so this is the 2D code. So this is also posted on Canvas, and so this is available for you. It's fully functional, so you don't need to change anything. But let's go through the structure of this code, and let's see the details, you know, and let's kind of match that up to kind of what we talked about, you know, by hand. Okay. All right, section 1. So section 1, we're just defining our variables here. So all of the important parameters we're going to define here. So you have LX, LY, NX, NY, dx, dy, dt, you know, all that good stuff, okay? And we create a space for the left-hand side matrix and the right-hand side vector as well, okay? And so I use A and B for that. Unfortunate, I wish I used better names for it. Okay. Next, we have the time loop. And so we see here that we have, we create variables for the current solution, sol cur, and for the next solution, sol next. Okay, so just like we did by hand. I have a few extra lines of code here. This is mostly just for the video, and so don't forget it. Don't worry about that. Okay, and we have t is equal to 0, so we initialize the time variable just like I mentioned. Okay. Okay, next we jump into the time loop, and so you can see here we have one giant loop here. So this will be 4 t step. This goes from 1 to nt. Okay, and you can see here this is where the time variable is going to come into play. So you can see here, we're computing the values for x velocity and y velocity. Okay. So there's 50 cosine pi t for the x velocity and sine pi t for the y velocity. Okay. Right, next we have the ij loop. And so now that we have the velocity values, we can compute the coefficient values themselves. Okay. We have a loop over ij. We have all the IDs here. Okay. Here is, you know, a lot of code here. But you can see here that, you know, these formulas here are exactly the ones that we have for our implicit Euler equation, right? So we have for the left ID, we have minus u dt divided by 2 dx minus our diffusion coefficient dt divided by dx squared, okay? And so on and so forth. Okay? And then we have the right-hand side vector here as well. Okay. And then from here, we have all the boundary condition loops. And so I'm not going to go through all these. These are all fairly straightforward because they're all Dirichlet boundary conditions. Okay. And finally, we solve for the solution. So we have this next solution is equal to a backslash b, and then we update the current solution. Okay, and then here I have some code just to do the plotting. And so remember, you know, Hakuna Matata, don't worry about the plotting stuff. And then finally, at the end here, we update the time variable t is equal to dt, okay? And then we close the bit file. Okay, so the moment I've been waiting for, probably the moment you have not been looking forward to, because you just want to go home. But let's go ahead and see what this looks like when we actually run the code, okay? And so you can see here we have an oscillating kind of flow field here. And so our x velocity is changing, you know, it's going right to left, and our y velocity is also changing up to down as well. Okay, and so what you get from this is kind of like a membrane here that almost looks like it's undulating. Okay, and so let me go ahead and play the video. So let's go ahead and where's the repeat? Settings. Whatever. I'll just play it over again. And so because our velocity is changing with time, now our solution is actually changing with time as well, right? And so we're no longer just kind of going towards a steady state. You know, we're actually having a situation where, you know, our velocities are actually changing with time, and they're actually oscillating back and forth, right? And so you get a solution that kind of looks like this. Right? And so for the homework, you know, I think for the homework, I gave you at least a couple problems where the solutions actually change with time. Right? So hopefully the lecture today was useful for you to kind of see how to actually use one of these time variables and how to actually incorporate that into your solution. Okay. All right, any final questions before we wrap it up for today? Okay. All right, so so both the codes that we went over today are posted online, so they are available for you to look at, especially as you're working on the homeworks. Okay. If you have any questions on the homeworks, definitely don't be afraid to ask. But if not, thank you guys for coming out today, and I will see you on Wednesday. If you haven't picked up your exams yet, I have them here in the class. So you can pick them up right now.
Because I feel like we need to get another time like this. Because we need to get it and we need to do ASAP, and then we need to work on.
Excuse me.
Yep, what's up?
For tomorrow's tutoring hours, do you think I can move that to Wednesday morning from
Okay.
8 to 10?
Yeah. Just send me an email just to remind me. I'll send an announcement after my next class.
Okay, and then can Fridays move from 9 to 12 to 7 to 10?
Yeah. Just send me an email and I'll send it all to you.
I appreciate it.
Yeah.
And then also, can I have, do you mind sending me the solutions to, I think it's homework 4?
Okay, yeah.
The most recent one.
Okay, yeah, I'll look at that.
I'll send you an email.
Okay, yeah.
Because that was a lot.
Yeah, thanks, Justin.
I appreciate it. Thank you.